Hi guys, welcome to Matrices 7. In this video, we're going to discuss about the determinant of a matrix. We are going to use determinants in a lot of places, especially in finding inverses. So the next session that I'm going to take is going to be about the inverse of a matrix. But to be able to find something called as the inverse of a matrix, we first need to understand what is the determinant, and that is the purpose of today's video or this particular video. My name is Srinivas. I am one of the chief mentors of Career Launcher Bangalore. I'm also your super senior from IIM Indore, hoping that you will all be my super juniors. All right, guys, let's go ahead. Right. So you're talking about matrices. I will start with the smallest of the matrix, which is a 2 by 2 matrix. If I have a matrix called ABCD, which is called A, capital A, then the determinant of this matrix A is represented in these two forms. It is written as DET in brackets capital A, that is det A. It can also be represented as A, B, C, D, just like a matrix, but in place of a square bracket, you actually use two straight lines like this. This represents the determinant of the elements given here. Now, mathematically, what is the meaning of this? So this is a symbol. Remember, this is a symbol. So what does it represent? In terms of maths, it represents, or it is given as the product of your primary diagonal minus, that is AD, minus the product of your other diagonal BC. So the determinant of a 2 by 2 matrix is very straightforward. It is AD minus BC, the difference between the products of primary diagonal and the other diagonal. Now, when it becomes, or when you're talking about determinant for a 3 by 3 matrix, it becomes a little bit more complicated than just taking the product and subtracting. Here, we follow a method called cofactor and minor method. So first, I'll explain to you what is the meaning of a cofactor, what is the meaning of a minor. So let us take this matrix A, B, C, D, E, F, G, H, I, which is a 3 by 3 matrix. Before we go on, always remember, determinants are calculated for square matrices only. Determinants are calculated for square matrices only. You don't have determinants for non-square matrices. So we are looking at a square matrix A, B, C, D, E, F, G, H, I. Now, cofactor is something that can be found for every element, which means I can ask you the cofactor of A or cofactor of B or cofactor of F or whatever element I have. So cofactor is a number associated with every element. Now, how do we calculate this number? So cofactor of, let's say, element A 2, 1. Okay, in general, I will write general form also. Cofactor of A I, j. This is given by -1 whole to the power of 2 plus 1. Here it is -1 whole to the power of I plus j into minor of 2, 1 into minor of 2 I, j here. I, j. This is called as a cofactor of an element. So let us understand what is the, forget about the minor part, we'll come to minor later. So what is a cofactor? Cofactor is -1 taken to the power of the sum of rows and column of that particular element you're trying to calculate. So if you want to find cofactor of A, it is -1 to the power of 1 plus 1, because A is the first row, first column, into minor of A, into minor of A. Similarly, if you want to find cofactor of F, okay, cofactor of F, it is -1 to the power of, now F is second row, third column, so it is 2 plus 3 into minor of f. This is called as a cofactor of f. So instead of the other way of remembering this negative sign is easy. One way of remembering this negative sign is plus minus plus minus plus minus alternately, plus minus plus. So instead of remembering it as minus 1 to the power of something, straight away if I ask c, it is plus into plus 1 into minor of c. Okay, if I ask you cofactor of h is minus 1 into minor of h. This is the fastest way to remember things. Now, I have been talking about this minor. What is this minor? Again, like a cofactor, minor also is for every element. So, if I want to write minor of A, the element A, then what you have to do is cut out your column of A, cut out the row of A, cut out the row of A. The remaining elements, write it in the determinant form, E, F, H, I. This determinant, that is EI minus HF, is called as the minor of A. It is called as the minor of A. Let's take another example. Minor of H. If I want the minor of H, what should I do? I will cut out the rows and columns of H. So, column, row. The remaining elements should be written in the determinant form. A, C, D, F. This is AF minus CD. This is called as the minor of H. Right. So now, if you combine this with your knowledge of cofactor, and if I ask you what is cofactor of I or cofactor of H, let's say, then cofactor of H is, now remember H is here. So plus minus plus, so plus and minus alternately, so it is minus 1 into, okay, minus 1 into minor of H. Now what is the minor of H? We just saw AF minus CD. AF minus CD. This is called as a cofactor of H. Okay, so this is how we find cofactors. Now, if you want to look at the determinant is actually defined as, any row you take, any row or any column, doesn't matter. Any row or any column you take, first element into cofactor of A plus second element into cofactor of B plus third element into cofactor of C. Now, if you apply this, what happens? A is as it is. Now, cofactor of F, first of all, cofactor of A is positive here. So, the minor of A is EFHI, we just saw. So, plus EFHI. Similarly, B is here. Now, cofactor of B, first of all, the sign of B is negative. And the minor of B, if you want to see the minor of B, what happens? You will have to cut out the B row and column, so DFGI, but with a negative sign. Similarly for C into minor of C. So the formula for your determinant is any row or any column, you take, each element multiplied by its cofactor. So it is sigma, that is summation of I, comma J, I, J, where J is going from 1 to N, and minor, cofactor of, or let's say cofactor is identified by capital A, I, comma J. Now only J will change, that is only the column will change, the row will not change. What does it mean? If this becomes too difficult to understand, let's simply put everything in a row should be multiplied with its cofactor. Every element should be multiplied by its cofactor. So we can also say the determinant from the second row. Also you can find the determinant. The answer will be the same. It is cofactor of D. So D into cofactor of D. What is the cofactor of D? This is plus, this is minus. So it is -1 into, now the minor of D. What is the minor of D? Minor of D. So this and this, if you take out, it is BCHI plus. Now in the same row you have to continue E into. Now if you want to find cofactor of E, the sign is going to be +1 into minor of E. Minor of E, if you take out the corresponding rows and columns of E, okay, if you take out the corresponding rows and columns of E, it is ACGI, okay, plus, then now F into, because in the same row, F into cofactor of F. F cofactor, first the sign is negative, so -1, and now multiplied by the minor of F. Minor of F will be ABGH. This and this will both be the same answers. So you can find the determinant of a matrix along any row. You can do the same process along any column also. Basically, it is nothing but sum of product of all elements and their cofactors in one row or column. Okay, right. So if you extend this to a larger matrix, the same property holds true. Determinant of A, if I take it along the first row, usually that's the habit, people take it along the first row. You will take A into, now the cofactor of A, so sign for A is positive, so it is positive, and this determinant, which is what I have written, right? Then the next element should be B into, so I got B. The sign for B, plus and minus, so it is minus, multiplied by the minor of B. Minor of B will be ACD. Oh, sorry, minor of B, right? Okay, my bad. This one should go. EGHIKLMOP, which is what I've written here. Similarly, C into minor of C and D into, actually not just minor, C into cofactor of C and D into cofactor of D. So that is how we will get the higher matrix. And you can see the calculations become more and more difficult as the order of the matrix keep increasing. Now, apart from this cofactor method and the minor method, there is a different method that we're going to see, which will help you solve the answer a bit more faster instead of remembering minors and cofactors and making sure that you are right, the correct positive and negative signs are there. Instead of doing all this, there is a rule of Sarrus which is particularly used for a 3x3 matrix. It is not useful for higher order matrices. Please keep in mind. This is only for a 3x3 matrix, and the rule says if you have a matrix A, B, C, D, E, F, G, H, I, then the first step is write down what you have, A, B, C, D, E, F, G, H, I. So this is your column 1, column 2, and column 3. This is the first step. The second step, repeat only the first two columns. Repeat only the first two columns. Okay, so this preparation you have to do. So write down what is being given to you, C1, C2, C3. Then just repeat C1 and C2. So you will get a series of alphabets like this or numbers like this. Now what you do, take the diagonal which I am mentioning, which you can see in the arrows, A, E, I. Take the product of these three numbers. Easy to remember, the diagonal starting from the leftmost and just coming down. Next, take the next diagonal. You can see over here, BFG. Add the product here, BFG. Take the third diagonal, CDH. Add these three diagonals. Now there are no more diagonals from left to right, right? All diagonals are taken care of. Next is the reverse order, GEC. This diagonal, If you can see over here, I'm changing the color into blue so that you can follow. I want GEC, this is the reverse order diagonal, and because it is the opposite direction or the reverse direction, I will call it negative. Go forward, take the next series of multiplication of diagonals, HFA, that is this particular diagonal. Again, it's in opposite direction, so negative. Finally, the last diagonal which is available, which is once again IDB. And again, it's in the reverse direction compared to the initial three, so it is negative. And here you will get your final answer. This itself is your final answer. All right. So this is called as a rule of Sarrus. You can do your determinant calculations very quickly using this simple rule. Right? Now, there are a few properties that we're going to use in determinants. There have been questions in actually IPMAT Indore where these properties were required to solve questions that have come. The first property is determinant of I. I is the identity matrix. In the previous session or in the previous video, I already covered what is the meaning of an identity matrix. Determinant of any identity matrix is always 1. It doesn't depend or it doesn't matter what is the order. The 2 by 2, 3 by 3, 4 by 4, any higher order matrix, determinant of identity matrix is 1. The second thing is determinant of A transpose is equal to the determinant of A. I'll explain to you what I mean. Now, I already explained what is the meaning of a transpose. So let's take a simple example. A, B, C, D. This is A. So what is your determinant of A? Determinant of A is AD minus BC. Let me write A transpose. What is A transpose? A transpose is A, C, B, D. Basically, your columns will be shifted to rows and rows will be becoming columns. So your determinant of A transpose, if you write, this is again the product of these two minus the product of these two. So you will again get the same answer. You can try this for a 3 by 3 matrix also, it does not change. So determinant of a particular matrix is same, the value is same as the determinant of the matrices transpose. The next property is determinant of A inverse. Now A inverse we haven't covered yet. I told you in the next class we'll be finding what is the meaning of A inverse. Right now, imagine that there is something called as the inverse of a matrix. Determinant of A inverse is 1 by determinant of A. Right? Determinant of A inverse is 1 by determinant of A. This is easy. The fourth property is easy for you to understand. When you're looking at multiplication of two matrices and then finding determinant, you can actually find separate determinants and then multiply. So the advantage is you are saving multiplication of matrix here. So as you can all understand that multiplication of a matrix is difficult. So it's not difficult, actually it's a little bit lengthy. So you can actually find determinants separately. You will get a real number and a real number, and ultimately it is a multiplication of two real numbers. But the more important part is the power of a matrix. This is where it actually really helps you. So if I say, let's say the matrix is 1, 2, 3, 0, 1, 1, 1, 0, 3. And I want you to find determinant of A power 4. Normally, if you do not use this property, you are supposed to multiply A by A, get an answer. Then this you multiply it with another A, so it becomes A into A into A. Then put another A into this. So 4 matrix or at least 3 matrix multiplications you have to do. Then you have to spend time finding a determinant. But because of this property, you can see that determinant of A power 4 becomes just find directly determinant of A, raise it to the power of 4. So you don't have to do matrix multiplication. You can just find what is the determinant of A and raise to the power of 4. That is what the property here tells you. The next property says determinant of K into A, where A is a matrix. Remember, K is a constant. It's a constant. right? So when you have multiplication by a constant, then you can write it as k power n into determinant of A. Now what is n here? N is the order of the matrix. Let me explain to you with an example. Let us say A is a matrix which is 1, 2, 0, 1, 0, 1, 2, 1, 1. So let me quickly find the determinant here. The determinant here, I will use a rule of Sarrus: 1, 1, 2, 2, 0, 1, 0, 1, 1. Now I have to write the first column again, 1, 1, 2, and the second column again, 2, 0, 1. So I want the product of these three, which is 0, plus I want the product of these three, which is 4, plus I want the product of these three, which is 0 again, minus I want the product of this, which is again 0, minus this product, which is 1 into 1 into 1, 1, minus the third product, which is 1 into 1 into 2. So the net effect is 4 minus 1 minus 2, which is 1. Now this is my determinant of A, correct? This is my determinant of A. Now if I want to find what is the determinant of 4 multiplied by A. Now if you remember the basic operations of matrix, 4A becomes determinant of, multiply 4 everywhere, so 4, 4 to the 8, 0, 4, 0, 4, 8, 4, 4. Now if you find the determinant here, that is my answer. But according to the concept or the property here, you don't have to find this determinant. You take the 4 outside and raise it to the power of 3. Why am I raising to the power of 3? Because A is a 3 by 3 matrix. So 4 raised to the power of 3 multiplied by determinant of A, which is 1. This straight away gives me 64 as my answer. So I don't have to multiply by 4 and finding the determinant. Now why is it helpful to me? If this 4 is not a neat number, let's say it is a fraction or something like that, then the entire matrix becomes fractions. And finding the determinant when there are fractions involved, it's a major headache. So a simple thing you can do is take this constant out and write it in terms of k power n here, and then simply find the determinant of A. That's how it is going to make your life easier. The last two properties are very straightforward. If all the row elements, one particular row elements or one particular column elements are zeros, then don't waste your time finding the determinant. The answer is 0. A simple example is 1, 2, 1, 0, 0, 0, 2, 3, minus 1. This determinant, if I want, if this is A, then determinant of A is 0. My job is done. Determinant of A is 0. Similarly, if an entire column is made of zeros, then also the answer will be 0 itself. The last property is something which is interesting. Now, if you remember in matrix operations, you could, so if you have A, B, C, D, E, F, G, H, I, and if this is matrix A, the matrix A, you can just interchange row 1 and row 2 without any effect. You will still have the same matrix, the meaning will not change. We discussed this. D, E, F, A, B, C, G, H, I. Correct? But when it comes to determinant, when you change, so when you have a determinant A, B, C, D, E, F, G, H, I, if you interchange the rows and columns, interchange two rows, row 1 with row 2. Let us say the first determinant answer is 6. Let us say the answer is 6 here. By some numbers, I'm getting 6. Then when I interchange the row 1 and row 2, it becomes D, E, F, A, B, C, G, H, I. The answer to this determinant will become minus 6. So whatever is the original answer, your answer now will be multiplied with a negative 1. So when you interchange rows or when you interchange columns, for one interchanging, one time you have to multiply it with negative. If there is another interchange, then another negative will come and you get negative into negative, your original thing will happen. So If there are two interchangings, one row interchange, then a column interchange, the answer does not change. The answer will still remain the same, right? So that is the meaning of a determinant, or this is the meaning of this property of the determinant. Okay, so the next property is splitting of determinants. Now, a determinant can be split into two determinants under one condition only. What is the condition? You should have two things which are getting added. So you have A1, A2, A3, you can see here is getting added to B1, B2, B3. Now this can be split as if A1, A2, A3 will come in the first determinant, B1, B2, B3 will not be there. But if you notice, this is your column 2 and this is your column 3. So column 2 and column 3 will come as it is. But whatever is the addition here, the first part of the addition becomes your first column here. And the second part becomes your second determinant first column. Here again, if you notice, the same C2 and the same C3 will come to you. Right? So this is one of the properties. Let's use a number for this. So if I have 2, 4, 6, 0, 1, 3, 4, 1, 2. If I want to write it as sum of two matrices, okay? If I want to write it as sum of two matrices, I will write my 4 and 6, 1 and 3, 1 and 2 the same. 4, 6, 1, 3, 1, 2. Now I can write this 2 as 1 plus 1. I can write this 0 as something minus something, anything. I can write it as 5 minus 5. I can write this 4 also into any two numbers. I can write this 4, let's say I will write it as 6 minus 2, which means 1, 5 and 6 come here. 1, negative 5, negative 2 come here. So it is, so by the way, please remember, this splitting is not restricted to only one column. You can do it for column number 1 or column number 2 or column number 3. The point is the other columns will not change. The other columns will not change. I'll give you another example. If I want to write 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to split the second column. So I will keep 1, 4, 7 the same and 3, 6, 9 the same. Plus I will write 1, 4, 7, 3, 6, 9. Now I will try to split this 2 as two numbers. I can write 2 as 1 plus 1. I can write 5 as 3 plus 2. I can write 8 as, let's say, 4 plus 4. So 1, 3, 4 come here. 1, 2, 4 will come here. Okay, right. The next property that we have is taking the common factor in a determinant. Now please remember, there is a difference between factor common in a matrix and a determinant. Now if you remember, a common factor in a matrix, if I have 1, 2, 3, 4, 4, 6, 2, 2, 3. Now in this kind of a matrix, I cannot take a common factor only from a column or a row, because if I write 2 into this, it means this 2 is getting multiplied everywhere, right? For every element is getting multiplied by 2. But in a determinant, it is slightly different. In a determinant, if you have a constant which is getting multiplied for all the elements in a row or a column, you can take this k outside. Okay, you can take the k outside. So it means if I have a determinant 1, 2, 3, 4, 8, minus 1, 2, minus 6, 3. Now if you notice, in the middle column, I can take 2 common from here. So I can write this as 2 into 1, 1, 3, 4, 4, negative 1, 2, negative 3 and 3. And the answer is still the same. The answer is still the same. It will not change. This is again an important property. It is not just about column or a row.
both a row or a column, the property is applicable. Okay. The next property that we're going to talk about is if two rows or columns are same, then the determinant is 0. If two rows or columns are same, then the determinant is 0. So it's a very straightforward property. So if you have 1 1 2 1 1 2 and 4 negative 1 negative 6, the answer is 0. The answer is 0. Right? Because the first row and the second row are both same. So any two rows or any two columns are same, then the determinant is 0. The last property that we have here is a determinant value does not change if a row or a column multiplied by a number is added to another one. So it is basically, if you remember, in row operations, in a matrix, I can replace my row 1 as row 1 plus k times R2. I can do this row operation. If you forgot, please go back to the initial videos where I discussed matrix operations and properties of matrix operations. Here the matrix does not change. Similarly, the determinant also does not change, which means if I have A, B, C, D, E, F, G, H, I, right? And if I perform R1 as R1 plus K times R2, what will I get? I will get a determinant, which is, remember, R1 becomes R1 plus KR2, so A plus KD, B plus KE, and C plus KF. And then DEF, GHI. Now both answers are same. The answers do not change. That is what the property tells you. Right, so with this, guys, I will be ending the properties of determinants. A lot of these properties have come in your IPMAT 2020. In fact, I am going to make a video on the questions that have come in IPMAT Indore for the last 2 years, and you will notice a lot of these properties have been used. Right? So thank you, guys. I hope the session has been interactive. It was a little bit lengthy. Usually I try to keep it below 20 minutes, but then it's a larger topic. So hope I'll be seeing you in the next class. Thank you and goodbye.